All right, fellas. Now, in the previous video, we have seen the measure of dispersion like range and quartile deviation. But again, we have seen the limitations of them, and the limitations are something like that. They don't consider each and every point. So, in this video, we'll move on to a better method of finding out the measures of dispersion. So, I'll just put it measures of dispersion. Right, I'll go for the same thing, but this time we'll have better measures of dispersion. Now, in case you want to understand what are measures of central tendency and what are various measures of dispersions that we have discussed so far, there is a link in the description. Please follow that particular link. You'll be able to understand range and quartile deviation that we have discussed in the previous chapter. Right, although what we're going to study in this video is not related to that. It's not related to that. Okay, so this will be slightly better. I'm working on my secondary screen, so that is why you might see me move my neck like this. But if you look at the dispersion, I think the dispersion there are better variables present over here. One is, of course, this is my mean deviation. Then we have something called as variance, and then we have something called as, I think all of us have heard of it, standard deviation. Right, these are the three things that we have. Right, now let's try and understand what do you mean by mean deviation. What is the meaning of mean deviation? Let's look at the formula. Right, the mean deviation actually is nothing but equal to a sigma, that is sum of xi minus x bar, a modulus of that, divided by n. That is the formula for mean deviation, and that is one of the bad things about statistics. It might look something which is relatively very simple, appear to be something which is, it appears to be complicated, when it is not. It's very simple. Let me look at another way of going for it. I'll go for let me take few quantities over here, like 10, 11, 11, 11, 12, 13, 16, 19, 20. Let me try and add them up. Okay, I have completely random quantities taken, guys. I'll just have to make their average integral so that our calculation becomes slightly easy. Okay, so 10, this is 33 plus 10, 43 plus 25 makes it 68, right? 68, 100%. 68 plus 16 will be 78, 84, 103, and the 20 is going to give me 123, and 123 on 9 quantities. I can see, right? 123 on 9 quantities. If I go for another quantity 10th, I think I can go for a 7 over here. That makes it like, the average comes out to be 13, and my job reduces. So 123 plus 13, I'll just check it out. 17 plus 33 makes it 50, another 25, 75, and another probably 35 makes it like 110, and 20 is 130. Fair enough. 130 divided by 10 is going to give me an average of 10. Now, what does mean? See, till now, range, what range does? Range does this. It just says that I'll take the maximum and I'll take the minimum. Minimum value uthaunga, maximum value uthaunga, and 20 minus 7 is going to give me a range of 13, which is okay. So your mean is coming out to be equal to 13, and the range is coming out to be equal to 13 as well. They're not related to each other, but yes, it is. Now the problem with range is that we have seen is that range के साथ problem ये है that if any one of these two turn out to be an outlier, for example, if I include another quantity over here as, let's say, 1, okay, my average will definitely change. But if I take this 11 quantities, the range will come out to be 20 minus 1, that is 19. Now range is a completely inappropriate method of understanding the data or representing the data, because range or the minimum value appeared to be a very outlier. It's an outlier over here. It's very distant from the mean. Okay, same is the case over here. If minimum and maximum, any one of them or both of them are outliers, range will cease to give me the appropriate nature of how spread my data is. Ultimately, in dispersion, what I'm trying to find out that how spread is my data, because I think we have already seen this in previous videos that if there is a mean like this and if there are data points like this and which are close enough around the mean, I can say that this is a data which is not very well spread. So the central tendency can be a better representative of the entire data. Whereas if I look at another data in which probably the central tendency remains the same, right? And if you look at it, the spread of the data is huge. Okay, I can say that this data is very well spread, or rather it's more spread than this one. Very well spread seems to be something positive, which is not, right? So I don't want the data to be spread too much, because if the data is spread too much, the central tendency will not become, the mean, median or mode will not become a good representative of the entire bunch of or group of data. Here it's a good expected value or a representative of my data, right? So range, that is why we need to understand how dispersed our data is. राइट, दैट्स वाई वी आर डूइंग ऑल दीज काइंड ऑफ थिंग्स. ये पूरा झंझट सिर्फ इसलिए है क्योंकि मैं समझना चाहता हूं कि मेरे डेटा मीन के अराउंड या मेरे सेंट्रल टेंडेंसी के अराउंड कितना स्प्रेड है. Right, that is what I want to understand over here. Now range is equal to 13, mean is equal to 13, simple as that over here. Now what I want to calculate in mean deviation is I calculate the deviation of every term with the mean. Here the deviation comes out to be equal to, let's say, the term minus the mean, that is 7 minus 13 minus 6. Here it comes out to be equal to minus 3. Here it comes out to be equal to minus 2. Here it comes out to be equal to minus 2 again minus 2. This is minus 1. This is no deviation at all. This will be equal to plus 3. This will be equal to plus 6. And this will be equal to plus 7. Okay. Now these are all the deviations. These are all the deviations. But I cannot add them along with their sign. Why? Because minus 6 will cancel out 6. So if I add the deviation of this point and let's say this point, the deviation comes out to be equal to 0, minus 6 and 6, isn't it? Which means that collectively the data is not deviated at all, which is a wrong indication again. What I need to do is to take the distance of every point from the mean, irrespective of whether the point is behind the mean or ahead of the mean. Okay, so that is why I take a modulus over here. So modulus of the difference between a number and the mean is nothing but its distance from the mean. I'm summing up all those distances and taking an average of it. Simple as that. That's the meaning of mean deviation. So if I sum it up over here, it'll come out to be 6, 3, it'll be, so the deviations, I'll just count the deviations over here. There are 6, 3, 2, 2, 2, 1, 0, 3, 6, 7. These are the deviations. Let's add them up. 9 plus 8 will be 17, 18 plus 3 21, plus 6 27, plus 7 34. 34 comes out to be the total deviation. And now I can say my mean deviation comes out to be equal to, the numerator comes out to be 34 divided by how much? 10. And I get mean deviation is 3.4. What do you mean by mean deviation? It simply means that on an average, every quantity is at a distance of 3.4 from the mean. So my mean is 13, but on an average, every quantity is 3.4 distance away from the mean. Okay, that is the advantage of mean deviation. Now, what is the biggest advantage of this? The biggest advantage of this is that it's considering each and every point's contribution in the entire data. The data consists of 10 points over here, and mean deviation takes into account the vote of each and every item over here, and that is why mean deviation is much better than range, or probably I think what we have studied, that is IQR, interquartile range. But interquartile range is a different application later on in data science as such, but as of now, to understand the dispersion in the data, I do not need this. I have got a better thing over here, mean deviation. Now, statistician thought over it and said that, wait. I think I'll just a minute, please. I think I've clicked on the wrong button. Just a minute. All right, guys, apologies. I think I, mistakenly changed the dashboard, but no worries. I'll put the data. Measure of dispersion. This is what we are doing. Apologies. Right, I'll not write everything because I think we've already seen mean deviation. Right, we have already seen mean deviation, and mean deviation is nothing but equal to, we have given the formula. I think you clearly understand the formula now, right? So mean deviation is nothing but sigma of xi, every term, minus x bar, right? and the modulus of this divided by the number of quantities or number of data points over here. We have already understood it. Now there is another term over here which is slightly more advantageous than mean deviation, that is called as variance. Now let me take the same data point over here. I'll go for something like 10. I think we have taken 7 as well. 10, 11, 11. I think 3 11s were there. Then there was 12. Then we have 13. Then we have 16. I completely missed what the data points were. Just a minute. Right. They were 19 and 20. Cool. So I think we have 10 points over here. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Excellent. And we had an average of 13 over here. And we saw that in the mean deviation, what we do is we calculate the deviation from every point and we take the modulus of it and we sum it up. That is a very nice approach, I must say, right? But variance goes one step further. What it does, it squares the differences. First of all, squaring has one simple advantage, that if you square, the sign will go off, right? We square it up. So variance says that don't do this. I'll just do one thing. Variance says, let's do one thing. Let's take the difference of every point from its mean and do not take the modulus, square it. Square it. And then divide this by n, the number of quantities, and then, so sorry, square root will not be taken over here. I am so sorry. थोड़ा सा भावनाओं में बह गए, but no worries. I think what we do over here is that we take the sigma of this. Right, this is the sigma. Variance is sigma of xi minus x bar whole square divided by n. That's how it comes out to be. That's how it will be, right? So instead of taking a modulus, it takes square. Number one advantage we have already discussed, that once I take the square, what happens is the negative 6 and positive 6, both of them are going to give me what? Negative 6, and the positive 6, both of them will give me what? 36. Simple as that. That is one advantage. What is the other advantage? What do you think? Pause this video, think for around a minute or so if you can, and think about what is the other advantage that I get. What do you think is the other advantage? And there is an advantage. Alright, now if you have given it a thought, the advantage over here is that by squaring, I punish, statistically, mathematically, I punish a point which is very far away from me. Because see, if the distance between these two, can I just say the distance between these two is plus 3 and plus 6? Right now, a deviation of plus 3 and plus 6, I'll say that the points are okay. This is giving me a deviation of 3 from mean. This is giving me a deviation of 6 from the mean. I mean, 3 and 6 are not that distant. It's okay. Both the points seem to be at almost the same distance from the mean. But if I square it up, I'll get this as 9. I'll get this as 36. And now I can see that the distance between the square is significant and substantial over here, which means that if I square it up, the difference or the gap between the 2 points when it comes to deviation increases further, and hence I'll be able to demarcate between the points which are very far and very close to each other. For example, if I look at, let's say, 3.1 square and 3.2 square or 3.8 square, if you look at it, if I just quickly calculate 31 square, it'll come out to be equal to 31 into 31, it'll be equal to 1 carries 3, 93 and 3 is 961, correct. And if I go for 38 square, there's a simple method over here, but let's not get over there. It'll be 38 into 38, we'll have 8, it's a 64. Oh, need to multiply this, I'm so sorry. I think 12, 144 carries 1, 12 subtracted from 25, 13 plus 1. It'll be 1444. Pardon me if I'm doing mistake, but let's see it. So 3.1 will have a square of 9.61 and this will have a square of this thing, 14.44. Now 3.1 and 3.8, these deviation seems to be not that far away, but these two, their square will be far away from each other. Hence, I'll be able to demarcate between these two and say that this is significantly deviating more from the mean over here. That's the advantage of variance. And the next one, which is our standard deviation, is nothing but, if we call it standard deviation, is nothing but square root of the variance. That is, the standard deviation SD has a formula that square root of sigma of xi minus xi minus x bar whole square divided by n. Okay, this is the case. Now this will not be square root over here, guys, because I think the entire thing is not squared, only the numerator is squared, so please be careful over there. Okay, so this will not be square rooted over here. So this is my standard deviations formula. Again, these three things are slightly better when it comes to measuring the dispersion in the data. Okay, let me draw this slightly better. Okay, that is standard deviation over here. All right, so this is what is the case over here. These are the three quantities which will give me better approach towards my dispersion, right? And they capture the outlier like anything. They punish the outlier like anything. For example, in this data, if I take, let's say, another point, let me go for 11, right? So I think I'll go for, let me go for the next sum is 165, right? So I'll go for 35. If I go for 35, some of these 11 quantities, the average will come out to be equal to, come out to be 165. If I divide by 11, it will come out to be 15, comes out to be the average over here. Now, if you look at it, 35 is very far away from 15, hence an outlier. Now, imagine doing 20 square over here. And imagine doing, let's say, this, the deviation over here is just 5. Although 20 and 35 as numbers are not that far away, but their squares will be, this will be just 25, the square of this and the square of this will be 400. So I've automatically, mathematically punished a point which is very far away from the mean. A few of you might say that, sir, what's the point? Right, what's the point? I mean, is it necessary? Because we can then keep on cubing it. Let's keep on increasing the power, but the punishment will be more. So the idea was not to punish very severely. The idea was to punish. Okay. So the point is, if you can go for a cube over here, the computational requirement of the formula will also increase very significantly. आपको हर deviation का cube निकालना पड़ेगा, which is a tougher task as compared to square. And if square has already punished those quantities, why to increase it for a very small incremental game of punishment? Right? So that's the entire point. This is called a standard deviation. Now I'll go for something, let me go for calculation of these quantities in Excel as well. Let me open up an Excel.